Hello everyone, we are starting chapter 18 in this video, which is going to introduce us to the basics of thermodynamics. This video is going to go over state variables, atoms versus moles, and temperature. So it's kind of just the basics of chemistry. So a lot of this will be a review if you took chemistry in high school. So we talked a lot, when we did fluids, we talked a lot about liquids and gases. These taken together are called fluids. So we're just going to add in solids into this, and these are the three phases of matter that we'll be concentrating on. So before, the way we were looking at things, solids acted very differently from liquids and gases. But starting in this chapter, we're going to concentrate on some properties where solids and liquids are very, very similar and gases are very, very different. So it's not quite so useful for us to separate into fluids versus non-fluids. If you think of the difference between solids and liquids versus gases, you know that solids and liquids are a lot more dense than gases. So just one look at this table. Air has a mass density of about 1 kilogram per cubic meter, whereas liquids and solids are all around 1,000 to 10,000 or so kilograms per cubic meter. So it's a very drastic difference in densities. And because of that, we're going to have to treat gases a little bit differently than solids and liquids. So we'll get to that, starting next chapter. A lot of what we're talking about in this video is common to both of them. One thing, okay, so the question we want to answer here eventually, which has more atoms, 1 kilogram of oxygen or 1 kilogram of water? In order to answer something like this, we're going to need to be able to talk about how mass relates to number of atoms. So we'll need to look a little bit at the periodic table. So that's this atoms versus moles part of today. But first, I want to just quickly mention what state variables are, just so you're familiar with the term. So state variable, so your book mentions that it's any parameter used to characterize or describe a macroscopic system. So you'll be hearing the words macroscopic and microscopic a lot. Microscopic is dealing with a single or just a few atoms or molecules, whereas macroscopic means it's of the size of like millimeters, centimeters, meters, something that we can see with our eyes. So it's going to involve a great number of particles. So a state variable is anything that is used to describe the state of the system. And we're going to focus especially the next few chapters on 3 of them. So three important state variables. Pressure, and this book tends to use a lowercase p for that. Pressure, volume, and temperature. So you probably had a sense of volume before coming into this class. We looked a little bit at pressure when we talked about fluids. We're going to get into more detail with that. And temperature you have some intuitive understanding for, but we want to be quantitative about this and really see the relationship among these three. So where we're going with this chapter is, the ideal gas law will be PV equals nRT, the relationship among these state variables. We'll come back to these variables. The first thing your book points out is the difference between mass density and number density. So you're familiar with rho from fluids, mass per unit volume. We're also going to look at number density, number per unit volume. So capital N is the total number of atoms or molecules. And like I said before, this is going to be a really, really big number. So you can have something like 10 to the 23 atoms per cubic meter, 10 to the 28 atoms per cubic meter, just ridiculously large numbers. And notice how this isn't set equal to anything. We're not giving this a label because we're not going to use it too much. So notice how we didn't call this like lowercase n or anything. So right now, just be familiar that it exists. To talk about the next few pages, I think it makes more sense to just pull up a periodic table. So why don't I... do that. Okay. Now I want to talk about some of the numbers that appear in this. But even more fundamentally, I want to talk a little bit about atoms versus molecules. So I mentioned both of these words. So some of these, so air. If I talk about nitrogen or oxygen, if I say I have a molecule of nitrogen or oxygen, so the air in this room tend to come in pairs. So you have one atom and it's just connected to another one. So you have all these atoms flying around in the air. So gas might look like this, where each one is paired up with something else and they don't break these bonds very easily. These are diatomic molecules. So at 1 atmosphere and temperature is close to room temperature, there are a collection of elements on this periodic table that exist as a diatomic molecule. So the ones that you need to know are the ones that I've circled right here. So hydrogen, nitrogen, oxygen, fluorine, chlorine, and bromine. If anyone says that you have any of these elements, they exist as diatomic molecules. They exist in pairs like this. And we'll see why this is important in just a second. This is to be contrasted with monoatomic atoms. So some things just exist as single atoms, and they're not paired up like this. This is monoatomic. So the ones that are monoatomic are helium, neon, argon, krypton, xenon, radon. These are the ones that we're going to focus on right here. So notice how everything on the last column here, these are called noble gases. And these have a complete octet. They have no desire to pair up, whereas these other ones do want to pair up. Okay, why is this important? Well, when we look at this problem, which one has more atoms, 1 kilogram of oxygen or 1 kilogram of water? When we say 1 kilogram of oxygen gas, we need to know it exists in pairs like this. So let's go ahead and try and figure out how many atoms. Let's just look at the first part of this, 1 kilogram of oxygen gas. So I'm going to start off here, 1 kilogram of oxygen. And actually, I'm going to leave it as 1 kilogram right here. You might remember from chemistry, you did relationships between the mass of a molecule and the number of molecules. So to do that, to go from a number of grams to a number of particles, we need to know some relationship between these two things. So for this relationship, we need to look at the periodic table, and we're going to focus on some of these numbers. So for oxygen, see that number 15.999? We need to know what it means. So that number there, oxygen 15.999, that's how many grams per mole. That's how many, there's 15.999 grams for every 1 mole of oxygen. So that's not per atom of oxygen. Remember, an atom is very, very small. It's a big collection of oxygen atoms. So we're going to hold off. So exactly what numbers to fill in here, we're going to hold off for just a second. And I want to first just answer what a mole is, because in order to read off what that number means in the periodic table, we need to know what a mole is. So 1 mole of anything, 1 mole of apples, is equal to a very specific number of apples, 6.022 times 10 to the 23 apples. And obviously, I don't have to just talk about apples. I can talk about anything. It's like saying if I have a dozen of something, that a dozen means 12. A mole means 6.02 times 10 to the 23. By the way, this is approximate. This number goes on, 6.022, I forgot the rest of the digits. This is handy because, this number is so big, it makes it's just a lot easier to deal with numbers that are more familiar to us, 1, 10, 1,000. So we don't always have to say times 10 to the, and then a ridiculous number. So it just makes things a little bit more manageable. Okay, so the way to read, so another thing we need to keep in mind is that oxygen comes in pairs. Okay, so let's see. So what this number means right here is that 15.9, oxygen has 15.999, and the units for that number on the periodic table are grams per mole. So if you had 1 mole of oxygen, that's how much it weighs. Now this is moles of oxygen atoms, moles of O. But oxygen exists as O2. Oxygen is a diatomic molecule. You know, all of these things in red are diatomic molecules. So if you have 1 mole of O2, the way we would convert that to a weight is to say, well, for every 1 mole of O2, it's going to weigh twice as much as 1 mole of O, right? If they're paired up, then this should weigh 32.0 grams. So 1 mole of O2, and I wrote this in a way that you can cancel out the units. A mole of O2 and mole of O2 will cancel out, and you're left with grams. So 1 mole of O2 is equal to 32.0 grams of O2. See how 1 mole of oxygen atoms is different than 1 mole of oxygen molecules. Right? So 1 mole of oxygen molecules is 32 grams. All right, let's go back to this. 1 kilogram of oxygen gas. So let's go back and figure out what that is. 1 kilogram of oxygen. Now, if someone just says oxygen gas, we know that this is O2. 1 kilogram of O2 gas. Now we want to go from, before we were going from moles to weight. Here we have to put the weight on the bottom, the grams, and the moles will be on top. So for every 32.0 grams of O2, there's 1 mole of O2. And for every 1 mole of O2, there's 2 moles of oxygen atoms. So you might complain right here that this is kilograms and this is grams. Well, in my head, I'm thinking instead of 1 kilogram, I'm thinking 1,000 grams. So to multiply this all out, I need to do 1,000 times 2 divided by 32. So my calculator here, I see that that is 1,000 times 2 over 32. Looks like this is 62.5 moles of atoms, of oxygen atoms. I'm just talking about the atoms separately, not the number of molecules, right? The number of O2 molecules would be half as much. There are 31.25 moles of O2 molecules. Okay, let's compare this to 1 kilogram of water. So how would we deal with 1 kilogram of water? So we're going to compare this to 1 kilogram of water is H2O. Now, this is tough, right? 1 kilogram of H2O. I don't know what to include right here, do I? I need to go from grams of H2O to moles of H2O. Well, 1 H2O molecule I can think of as 2 hydrogens and 1 oxygen. So all of these things connected together, that's 1 H2O molecule. So I just need to figure out how much this weighs. I can just add up the contributions from each of these, right? So this is 2 atoms of hydrogen and 1 atom of oxygen. Going to our periodic table, I see that each hydrogen is 1 gram. So I'm going to imagine I have 1 mole of water molecules. This is going to be 1 gram from each of the hydrogens, so that's 2 grams, and then 16 from the oxygen, so that's 18 grams. 18.0 grams of H2O for every 1 mole of H2O molecules. And then for 1 mole of H2O, there are 3 atoms. And now I'm not writing oxygen or hydrogen because it's including both of them separately. So 1,000 times 3 over 18 looks like it's 167. Oops. So notice I wrote down 1 mole of O2 and I wrote down 3 atoms. It's 3 moles of atoms. Remember, a mole is a big, big number. Right? So it's 167 moles of atoms. Right? 2/3 of them are hydrogen atoms and 1/3 of them are oxygen atoms. So it looks like the water has more atoms. Which one has more atoms? Okay, so the periodic table, it gives you a lot of information. That number underneath is the atomic weight in grams per mole. The number above, so for example, for oxygen, so we read off 16 grams per mole. The 8 is the number of protons in the nucleus, and also the number of electrons for a neutral atom. And so the weight minus the number of protons gives you the number of neutrons. So that weight is a combination of the protons and the neutrons in a nucleus. Okay. So this number, Avogadro's number, your book calls that Na. And one important thing here is that N, we're going to use the symbol N for the number of moles of substance. So from the example problem, so 62.5 moles of O atoms. So I might say that N is equal to 31.25 moles of O2 molecules. And really we care more about molecules. So when we write down the ideal gas law, PV equals nRT, the N is going to refer to number of molecules. So if you have a diatomic gas like this, we want to this will act a lot of times like one object. This acts like a single object for a lot of things that we're going to do in thermodynamics. And so that's why we just say number of molecules. So this thing that I just circled is 1 molecule, or this is 1 molecule. So a molecule could be 1 atom, it could be multiple atoms. It depends on how they're bonded. But each of these are 1 molecule. Some textbooks are strict and they say, well, a molecule has to be, at least 2 atoms. So they would say the oxygen O2 is a molecule, and a helium atom is not a molecule. But I'm going to use the word molecule generally to refer to either of these 2 things. Okay, that gives us a quick rundown of what you need to remember from chemistry. So now we can maybe quickly go over temperature. So temperature you have some intuitive notion for temperature as the hotness or the coldness of something. And you're used to measuring it in terms of either Fahrenheit or Celsius. So to define a temperature scale, you need to know two facts. So to define either the Celsius or the Fahrenheit scale, if we knew what numbers correspond to the freezing point of water and the boiling point of water, then we would have our temperature scales defined. So the boiling point of H2O and the freezing point of H2O. We're going to talk more about phase changes later on, but H2O is the chemical composition for ice, for water, for steam. So these transitions happen at particular temperatures. Now for Celsius, the freezing point is at 0 degrees C, and the boiling point is at 100 degrees C. So 0 degrees C or 100 degrees C. For the Fahrenheit scale, these points correspond to 212 degrees F or 32 degrees F. So the person who invented the Fahrenheit scale, they thought that the coldest temperature wasn't the freezing point of water, but they created a brine solution, so a really salty solution, which lowers the freezing point, and the coldest they could get was about 0 degrees. So they just called that coldest thing that they could achieve 0. So this defines, so we're going to look at linear temperature scales. So we can imagine, so from 0 to 100, if we break this up into 100 pieces, I'm not going to write out 100 lines, but imagine 100 lines right there. That tells you what the Celsius scale is all about. For the Fahrenheit scale, there's more of them. So 212 minus 32 is 180. So there's 100 lines here, 100 steps to get up to here. On this one, there's 180. So 180 steps on this Fahrenheit scale, whereas that same increase in temperature is only 100 steps here. So this tells you that 1 Celsius degree is bigger, the jump here is bigger than the jump here. So 1 degree Fahrenheit and 1 degree Celsius are not the same temperature change. And the relationship between the two, so because this is 100 steps and 180 steps, it looks like the ratio is 180 over 100, or 18 over 10, or 9/5. That's exactly where this factor of 9/5 comes. So if we want to relate these two temperature scales, so in other words, I have some number here, call that the temperature in degrees Celsius, and we want to write what that is in terms of degrees Fahrenheit. We need some equation relating these two things. So the relationship is going to involve this factor 9/5 for the ratio, and then there's an offset of 32 degrees. And that's exactly where this equation came from. Okay, there's one temperature scale that you might not be as familiar with, and that is Kelvin. So one important fact about temperature is that we're going to see later on this chapter is that there's a linear relationship between temperature and pressure. And so one way of measuring temperature is to see what they did right here. They put a gas in some liquid, and the liquid is the system whose temperature we're to measure. And you can read out the pressure of the gas. The colder the system is, the lower the pressure is. And it turns out it's a linear scale, but the lowest pressure you can get is 0. So there is a limit to how cold something can get. There is a lowest possible temperature. The Celsius scale can certainly get negative, and the Fahrenheit scale can certainly get negative, so you can have negative temperatures here. But we'd like to define another temperature scale where the lowest possible temperature is 0, so that all temperatures will be positive. So an absolute temperature scale is one that starts at 0 for the coldest possible temperature, and all other temperatures are positive. So the SI unit for temperature, the most common temperature scale, is an absolute temperature scale, not one of these two. So Celsius and Fahrenheit are not absolute temperature scales. The one that we like the most is Kelvin. Kelvin is an absolute temperature scale. And its step size, so it starts off at 0. So this is called absolute 0. Absolute 0. The freezing point of water is up here, and the boiling point of water is up here. So freezing point and boiling point. So we start off at 0 Kelvin. And we're defining the Kelvin. Remember, we need two facts to define a temperature scale. One of our facts is that it's going to be an absolute scale, so it starts off at 0. And the other fact is that the size of the step here is going to be the same as the Celsius one. So there's going to be 100 steps from the freezing point to the boiling point. So with those two facts, we know that So we can, if we extrapolate down to 0, we have to call the freezing point of water 273 Kelvin, and the boiling point is going to be 373 Kelvin. Remember, if it's 100 degrees Celsius, to go from the freezing to the boiling point, it has to be 100 Kelvin as well. And notice how I'm not using the word degree for Kelvin. We just say Kelvin rather than degrees Kelvin. Okay, so when we do the ideal gas law, PV equals nRT, you have to plug in T in terms of an absolute temperature scale. That equation is only going to mean something for absolute temperatures. So for temperature changes, right, if delta T is 100 degrees Celsius, that's the same thing as degrees Kelvin, or sorry, Kelvin, not degrees Kelvin. So delta T's could be in Kelvin or Celsius, but anytime you have an equation that just has T, you have to use Kelvin. Okay, so PV equals nRT, you cannot plug in Celsius or Fahrenheit for that one. You have to plug in Kelvin. Okay.